Recordings rolling. It is Thursday, October 16th. So yesterday I was taking you guys through these universal gravitation posters. So I'll give you guys a quick recap of the main important ones. And then there were a few more that I didn't quite get to at the end of class. So I'll cover those with you guys. Then I gave you guys this rotational lab, uh, um, yeah, rotational kinematic lab paper. I guess you guys have that. And you guys have turntables. So near the end of class, we'll get started on that. We won't finish the whole lab today, but I'll walk you guys through. But we'll get it started if we can. Okay. And then now, honor students, don't worry about this, but since I'm doing recording here, for my AP students, they do have an AP assignment that's due on Monday for AP classroom, so they got to do that. All right. So let's do a quick review yesterday. So we're looking at this universal gravitation. This is what Isaac Newton figured out. He figured out he was looking at the moon orbiting the Earth, right, which we're also going to recap orbitals, some good orbits, right? And he looked at an apple falling from a tree. He said, "Yeah, I think that's the same phenomenon as driving both of us." So he called that gravity. Now, what's the value of gravity? Well, gravity, we'll call that a force due to gravity. Uh, now, he has been working with this for like a few months. Couldn't that be your weight? Your weight, right? Right. So, like this 500 grams mass, 0.5 kilograms mass, this weighs 5 newtons, pretty close. Okay? But now we're looking at a universal form because this would have the same mass on, say, the moon or Mars. Like, this would feel the same. But if I pick it up, it has different weights on different planets. And that weight, which is this force, has to do with the mass and radial size of the planet. So, see if I can put this together. It turns out this force is directly proportional to each mass, so you multiply the mass together. So if it's the Earth and the Moon, for example, it'd be mass of the Earth, mass of the Moon. Okay? You divide by the distance between them squared. That's called an inverse square relationship. And then to tie it all together and make an exact equation, you need this universal gravity constant that von Velde figured out. You guys remember 10 to the minus 11, really tiny number? Okay? So here, let's run some proportions. See if you guys figure this out. Guys, what if the mass of the Earth was 3 times as massive? What would happen to this force? If you throw a 3 on the sim, the force becomes, 3 times as strong. So 3 times. What if both the Earth and the Moon? What if this mass and this mass are each tripled? Triple is how many times the force? 3 times 3 is 9. 9 times the force. Aha. All right. How about this? What if you took the distance between Earth and the Moon and you made it 3 times as big, which goes off the screen. But what if this R was 3 times as big? What would the force be?
1/3.
Huh?
9 times.
1 over 9. 1 over 9. Right? So okay, so it's in the denominator. So as they're getting further away, the force getting weaker, right? Getting weaker, right? But it's also squared, hence inverse square relationship. So you get 1 over factor of 3 squared, that'd be a ninth the force. Okay? That's a proportion there. Do that. All right, then here, I'm gonna flip ahead a little bit. Okay. So could you do this? Because no matter what your mass is standing on the Earth, doesn't everybody have the same gravity field? Here, like if I take this whole box of lab lights and just went clunk and just like dunk these over the edge of the table, wouldn't they all free fall at the same rate? Okay. And that's sort of embedded in here. If I just divide each mass out, what are you guys looking at right there? That's not a force anymore. That's called the what? Gravity field. Yeah, gravity field, lowercase g. Because m times g could also represent weight. Okay. So that looks like this right here. So gravity field for this guy standing on Alaska is gm over r squared. Okay. Now, what about orbital speed? Like how fast do you have to send a satellite to keep it in orbit? This goes back to 1957. You guys remember that? First time we did that. Okay, so orbital speed. Now, this satellite here has, this is just review from yesterday, has how many forces acting on it? One. Its own weight. That's it. Which actually is this force right here, isn't it? Right? And the fact it's moving on a curved path, right? So it's going so fast to the side that by the time it free falls down towards it, because it is in free fall, it's just on free fall on a curved surface. Okay? It doesn't actually ever get any closer to the starfish. Huh, that's interesting. For a circular orbit, that would be true. Then that gravity force is also acting as a what kind of force to keep it on a curved path? What force keeps something on a curved path? It starts with a C. Centripetal. Aha. Okay. So that's the start of this proof. So here, just over. Right? So yesterday, did I take you guys through this proof? I think I did. Okay. We're trying to derive orbital speed from scratch. So centripetal force is provided only by the gravity force. Now, for centripetal force, guys, do you remember from your last lab what expression was the answer to that last line? Centripetal force equals what? What times what squared divided by what? mv squared over r. Hey, that's that. And this universal gravity, well, that's that. Okay, so you guys see what that would get at? Okay. And then from there, the mass of the satellite cancels. One of these r's, take square root. That's the orbital speed. Here, and let me push this into the calculator for you guys. So what's the orbital speed around the Earth? So I'll do square root. I'm going to open up some extra parentheses. As soon as I close the parentheses, stop square rooting. Just remind you guys how to do this. So g is 6.67 times 10 to the negative 11. I'll put all these in SI units. The mass of the Earth is 5.98 times 10 to the 24. And then divide by, and then in parentheses, because I've got more scientific notation down here. The radius of the Earth is 6.38 times 10 to the 6, and that's meters. Okay? 10 to the 6, that's like million, right? Okay, so I get 7,900 and something. Okay? So if you got it going that fast, you're the surface of the Earth, yeah, you can go into orbit. Okay? That's how fast low Earth orbit basically is. Okay. All right, so that's a recap from yesterday. You saw this. Escape speed, I can't prove this until we get to conservation of energy, so hang tight for that. Okay. I think I just shown this right near the end of class, and then the bell was ringing. And so we'll pick up with that here. Now, this starts out kind of an abstract academic idea, but this is going to actually be helpful later on today. So what if you're creeping around the galaxy, you come across some planet, you're walking around on the surface, you say, there's something weird about this planet. So you dig a hole and, whoa, it's hollow. The whole thing's hollow. We got an eggshell planet. Eggshell planet. You guys, can you walk around on the surface and the mass of this planet effectively pulls you towards the middle? Yeah, the center of mass is here, so you can pull towards the middle, as long as you're walking around on the outside. But, guys, once you step inside, something weird happens. And I picked sort of a random point. Guys, what if you're at some point where whatever distance you are from the surface on the right, you're 3 times on the left? And my question is going to be, where are you attracted to inside this spherical shell? Okay. Right. Do you guys see that up and down would definitely cancel out by symmetry? You're not pulled upward or down more. Okay. What about right versus left? That's the real question. So on the right, here's my universal gravity. You got gmm over r squared, where the lowercase m is your own point mass, and this big M represents. Ooh, do you guys see like a cone shape? See how you like draw a cone? Draw a cone. Okay. There's some mass here, like some shell piece that's probably pretty close to a circle, isn't it? Okay. Has some mass there. Okay. Now on the other side, see you're further away. Did this wedge just look bigger? So what counts for more? Right? Which way are you gonna pull? Okay. Well, guys, if you're 3 times further away, is this 3 times the diameter of the circle compared to this one? Right, 3 times the diameter. And guys, 3 times the diameter is how many times the area? 9. Aha, 9 times. Right? Right. And then suppose they have the same thickness, they're both like 1 foot thick or whatever. Right? So that would translate to 9 times the mass. Right? But also 3 times farther away, when you do gm over r squared, that r is also times 3, and that also gets squared. Ah, do you guys see 9 over 9 right here? 9 over 9. So it cancels out. And I could have picked any point inside the spherical eggshell, and it have gravity figures here. So okay, now how's that helpful? Well, it's going to be part of the explanation for this one. So what's the gravity field around any planet? And you guys see this note here says uniform density? Right. Now this is a real simplification of this class. Do you guys think realistically the density probably changes as you go like way, way down? Yeah, right. We're going to assume it's like the same Earth dirt all the way through. Let's just go with it. Okay. What would the gravity field look like? Right, so we're starting on the surface. Hey, have all of us lived our entire lives at the surface of the Earth? Mm-hmm. Yeah, I think so. Right. So I'll call that distance capital R, like the fixed radial size of the planet. And the gravity field each of us experience is 9.8 meters per second squared. Can that be this value right here? If this was Earth, that would be 9.8 meters per second squared, wouldn't it? Okay. Now, what if you climb a tower that is 1 Earth radius tall? 1 Earth radius tall. In terms of the universal gravity formula, by what factor has your distance changed from the Earth? A factor of, like right now, are we all effectively 1 Earth radius from the center? Right? But if you climb a tower that's just as tall, yeah, how many you effectively doubled your distance from the center of the Earth? Right? And let's think how that would play out. Whoops, did I put that away? It's okay. So I'm thinking about this one right here. Okay. Guys, if you double your distance, what happens to the gravity field? It'd be 1 over 2 squared. Oh. Yeah, one quarter, right? Right. Doesn't make sense if you're getting far away. The gravity field is getting weaker, right? So it's like 1 over something. So I think that see if this is like the full gravity field at the surface, I go to like 1/4 of that. Okay, 1/4 of that. Okay, that should represent 2 Earth radius. Yeah, it's that point right there. You see that? If you double the radius, right here, point or your distance, I should say, right? Yeah, that is 1/4. You see that? 1/4 of the surface gravity. Right. And then if you take off in a rocket and fly further away, but by the time you fly all the way to like Mars, does the Earth pull on you anymore? Hardly at all. It's tiny, tiny, tiny. Okay. Guys, this part of the graph right here, is this asymptotically approaching what number? Yeah, zero, zero. So, but when you get really far away, it's like almost nothing. Okay. So this is like 1/r², isn't it? And if you graph 1/r², it would take that shape. You guys think about that shape? Okay. Now let's tunnel downside. Ooh, look, this guy has a shovel. Right. What if you go all the way to the center of the Earth? Let's start with that one. Guys, in the center, let's say you bring a scale with you, and you stand on the scale, or you try to stand on the scale. What does the scale read right at the center?
Zero.
Zero. Yeah, and there's no floor to stand on. Are you floating around like an astronaut? Yeah, you're floating around like an astronaut. Okay? Because every grain of sand on Earth pulls you a different direction, so it all cancels out. That's this point right here. So I'm saying at the very center, there'd be zero gravity field. So you're floating around. Right. Now, the tricky part of this, do you guys see this straight line right here? I'm going to make the case to you. We're going to do a little tricky math, and I especially want to record this for my AP students, but you guys get to see this too. Maybe I'll do a little faster. Yeah, right. Is make the claim that as long as there's uniform density, as long as it's the same Earth dirt all the way through, that if you're, for example, halfway from the center and halfway from the surface, you should have half the gravity field. And if you're a quarter way from the center, maybe you have a quarter of the gravity, and so on. So it should be proportional. The gravity field should be proportional to your distance from the center. Now, how can you do that? Okay. So let's get this picture going. Okay. So let's say you are like halfway down to the center. Okay, so you're standing kind of this dash line elevation. Throw him a little stick figure right here. Okay, so he's got his little shovel right here. Okay. So remember the full radius of the Earth is capital R, and maybe this guy's standing at lowercase r. He's like halfway down. Okay, is it? So again, I'm making the claim that you should have half the gravity field, but how can I show that? Okay, so ooh, how about this, guys? What's above him in elevation? Is it like all this dirt? But could you just divvy this into like a billion eggshells? Eggshells? Oh, it's the eggshell planet back again. Right, isn't this guy like isn't sort of like a series of like Russian nesting dolls, like one inside the other? And eggshell planet doesn't every single eggshell cancel out? And what I'm trying to get, you guys see that? Okay. Right, every eggshell cancels out, and what you're left with is just whatever ground is beneath him in elevation. And I'll color that in pink ink right here. Okay. It is as if he's standing on a planet that's just that pink region. So it'd still be a 3D ball, it's still a sphere, right? But it's just that. And nothing else above him counts because it all cancels out. It's a series of eggshells. Okay. Is that right? Okay. Another way you might see this question framed is, right, what if there's a planet that has the same density as Earth, but it has half the radius? And half the radial size, and you're walking around the surface, what gravity field do you feel? It's the exact same answer as whatever we're about to do. And gravity field, I know, is universal gravity constant, mass of the planet, right? So this mass of the planet going divided by the distance to the center squared, right? Right, center of the surface. But this mass is sort of changing because here maybe I only care about the peak mass, not the entire mass of the original planet from the surface. Okay? So let's bring in, do you guys know density is mass per unit volume? Okay, so here's density. Okay, here's mass, and here's volume. Okay, I'm going to rearrange that. So Greek letter rho is density, like the density of Earth dirt. I'm going to rearrange this to get mass is equal to density times volume. That's okay, right? That's good. Okay. Now, who remembers? Guys, what is the volume of a sphere? What's the volume of a sphere? 4/3 pi r. Guys, any volume is always r to the power of what?
Cube.
Yeah, 3. Yeah, cube. 3. There you go. Pi space. Okay. Now, even if you didn't know the 4/3 pi, that just makes a cube into a sphere. Right? That's okay. The important part is definitely this r to the power 3. Actually, if that's all you know, that's all you need to prove this graph right here. Right? So I'm going to take, oh, actually, here. This would feed into this. And then that expression further feeds into, right? And the idea is that I'm trying to get gravity field strictly in terms of R, or as much in terms of R as I can. Right now, some things don't have to do with R. Like pi has nothing to do with the radius. The density has nothing to do with the radius. The gravity constant has nothing to do with radius. Right, but the mass does. Right, like the greater the radius, the more the mass of the planet. That would be true, right? So put this all together. So gravity field equals. So I got gravity constant. I got m is rho times v. So rho times v, but v is 4/3 pi r to the 3. See, I did like a bunch of substitution there, and I'm still dividing by this r squared right here. Right, is that okay? Right. It is substitute this into this, substitute that into that, and then it looks like that. Okay. Now, ooh, guys, what is this right here? Yeah.
I don't know the sign.
Yeah. Guys, what's r to the 3 divided by r to the 2? R. So I could say gravity is universal gravity constant times the density of Earth dirt. I got a 4/3 pi in the mix. And this just boils down to R. Just R. Right? Right. Now, let's take a look at this. Right, so gravity field, that's like the y-axis on this graph. And then R is the x-axis. Isn't this like y and x? Something like that. Y and x. Right? Gravity constant, that's a constant. Earth dirt density, that's a constant. 4/3 pi, that's a constant. Guys, all this right here is just a series of constants. Right? Isn't this like y equals kx? And guys, y equals kx. What shape does that graph take? Straight line. Aha, straight line. You guys see it? Right, that's where the shape comes from. Right? Furthermore, do you guys see what the slope of this line is? Okay, yeah, the slope of this line is all these right here. Yeah, g rho 4/3 pi. That's the slope of this line. Okay. All right. Okay, so maybe a little technical, but that was a fun adventure. Okay. I got a couple more of these for you guys. So these are a bit more trivia, but these are fun to know. Okay, how do tides work? Right, so in our calculations in this class, we tend to do like center to center, or we're going to treat the Earth as a point mass at its center mass, and same thing for the moon, right? But realistically, the Earth is actually spread out over a volume. And you guys think that there's a surface that's closer to the moon and a surface that's further away, hence they actually feel a little bit different gravity forces. Right? So the close side to the moon feels a greater force. In the middle feels like the medium force, and the far side feels the smallest force. Right? Okay. Now this picture's not to scale. You guys know the moon is like 60 Earth radii scooted over, right? But the idea is right, right? Okay. So, yeah, so the Earth will actually bulge a little bit like this, and since the Earth is mostly covered in water, that's what the tides are. Okay, so you got there'll be two tides every day. Now on the side of the moon, do you guys ever notice that only one side of the moon ever faces the Earth? Yeah, because before 1957, we had no idea what the other side of the moon would even look like because we never seen anything into space. Okay? The moon is what's called tidally locked, and this is common throughout the universe too. So actually, even just within our solar system, there are a lot of moons that are tidally locked to the planets that orbit. Okay, and last one of these posters for gravitation, Lagrange points. So do you guys think there's a point between the Earth and the Sun where gravity fields sort of cancel out? Like the Sun pulls to the left, the Earth pulls to the right, and they cancel out? And that might be a useful place to park some satellites. You could do that. Right? So if you wanted the like same place relative to Earth, you could do that. Right? There's also this L2. Now, the rest of these have to do with the orbital mechanics. So guys, do you think there's a point out here, L2, where the Earth and the Sun are both pulling to the left, but maybe you can sort of get dragged along and you kind of follow the Earth, so you never actually fall any closer to the Earth? Do you guys see that? Right. Do you guys know the James Webb Space Telescope was set up a few years ago? You guys know that? Yeah. There's all kinds of cool astronomy photos that are published that are new just in the last few years. That's actually orbiting the L2 point. It's actually orbiting, right? Which is a really good place to be because it's somewhat blocked by the Earth. It can be in the Earth's shadow, right? It could block the sunlight, and it can see all of space out here, see all the universe. Right? Now, there's also an L3. So the Earth and the Sun are both pulling to the right, so it actually kind of falls along. So there's like little tiny asteroids that might be around here, right? Get sort of vacuumed in this position relative to the Earth. Right? I don't think there's really anything significant out there, though. People used to think there might be. There was actually speculation for a long time there might be sort of like an anti-Earth out here that we could just never see. But, well, since satellites, we know that's not. Since space probes, we know that's not the case. Right? And finally, who these points are named after, a guy named Lagrange actually did math to show that if you make equilateral triangles, you can also get an L4 and an L5 point, and I can show you on an animation that that's true. So here's our solar system from above. Here's our rocky planets in the middle. Here's Jupiter going around. You guys see big old Jupiter going around? Right? Guys, what are all those pink dots?
No.
Asteroids. Aha, asteroids. Right, that's the asteroid belt. But hey, whoa, what is this? Guys, is the asteroid belt sort of triangular-ish? Do you see sort of a triangular shape to it? Yeah. So here's the opposite side of Jupiter. That's the L3 point between Jupiter and the Sun. The biggest masses in our solar system, well, by far, it's the Sun, and second is Jupiter. So those are driving a lot of the mechanics of our solar system. Right? And then, here's what about these green patches? Are those also asteroids, do you think? Yeah. No, the name of those, it's called the Trojan and the Greek asteroids. Those are at the L4 and the L5 points between Jupiter and the Sun. Yeah, that's it. So you see the Lagrange points in action there. Right? Right. All right. All right. So, all right, let's go to turntable physics. So you guys have a turntable and a lab page. Uh, Now, my earlier classes, I was able to get about halfway through this or so, so I'll get you guys as far as I can today. So, everybody ready to do this? Okay, so, you guys have one turntable per team, but every student has a lab page. So, write your name. I'm going to write period 7. So, I can pick up here tomorrow with you guys. Okay. And I'll try to get you guys approximately where my other classes are. So, we're on pace here. Okay. All right. So, what we're doing with this turntable. The story goes like this. I'm going to put a math down. Now, I'm going to use a Roosevelt right here. You guys probably have some math, maybe a coin nearby. Okay. And all I'm going to do is, here, let me point out exactly what it says. It says 3 revolutions at constant angular velocity, and then release and allow to slow to a stop. It's a two-part story. That's it. Can you guys see that? Give it 3 revolutions and then let it slow to a stop. Okay. I'll show you guys exactly what that looks like. It goes like this. So 0, 1, 2, 3, and I pick my finger up and I just let it naturally come to a stop. Right? It takes some time to do that. Okay, so like that. Okay, slide those for you can see, and then Roosevelt ends up over here. That. Okay, that's pretty straightforward, right? Pretty straightforward. Okay, and what we're going to do is we're going to make sense of all these kinematic values. So, what's the radial distance from the center? Is the first question. Then I gave you some equations here. I'll pull up the posters and remind you guys what those are and how they work. Okay, let's say how far is it turned? Eventually, how far has the coin moved? Okay, and then there's a bunch of questions for that, and I'll eventually move guys to be making some graphs. Make some graphs. So, first question: what is the radial distance in centimeters? So, here, I'll just have this guy parked here, and can you guys find the center of your turntable and measure out how many centimeters it is to your coin, or in my case, my Roosevelt right here. This guy's 11 centimeters out center to center. So I'm going to write 11 for 11 centimeters. Did you guys figure out what your radius is? Now, yours doesn't have to match mine. You can do 8, 9, 10, 11, 12, 13 maybe, if it fits. Right, guys see that? So I'm going to put Roosevelt at 11 centimeters. 12 centimeters. Okay, yeah, you can do 12. Okay, that's all right. Okay, but did everybody have their radius size? Just like I do? Okay. Right, you guys good? Right. Then now I'm saying 3 revolutions. But guys, actually, you know what? Let me show you these formulas. Right, so we got a batch of formulas right here, which are the same as on these posters. I think you guys have seen these recently, maybe. But here, let's do a review. So here's my turntable. What if I have 3 different points going on? So here's how far in a linear sense it goes, like odometer of a car adding up to driving to circular racetrack. Here's how far the turntable turns, and the connection is either multiply by r or divide by r if you're going the other way. Okay. Okay. The catch is though, guys, theta, if you want to use this formula, theta has to be in what unit? Radians. Right? Now, you probably have a protractor within reach, and the protractor measures in what unit? Degrees? You think we'll have to probably convert degrees to radians at some point today? Yeah, so hang tight for that. Sorry. There's also for speed, so angular speed versus linear speed. Again, very simply multiply by r to go from one to the other. And there's also an acceleration idea. Okay. So speed is how fast. Acceleration is something to do with like speeding up or slowing down with rate that's happening. And this picture is showing you 1 radian, which is about 57 point something degrees. Okay. So when I say 3 revolutions, guys, 3 revolutions, how many radians would that be? How many radians is 1 revolution? Pi. 2 pi. Right. You guys remember circumference equals 2 pi r? You guys remember that? Right. So 2 pi radian is 2 pi like 6.28? Can you see it would take about a little more than 6 of these wedges? So 6 and 6 point something to complete that. Right.
So I know one revolution is 2 pi radians. So how many is 3 revolutions? 6 pi. Did I see 6 pi? Okay. So that'll be a good number for calculations later. Okay. So remember, I'm going to let this rotate 3 times. I'm going to time it while I'm doing that. So I'll clear out my stopwatch. Okay. So again, all I'm going to time on the stopwatch is how much time does it take to do those 3 revolutions at constant angular velocity. And then as soon as I let go, I'm going to stop the stopwatch. Now after that, the turntable will still turn, and it's going to slow to a stop. Okay? Okay. And then just keep an eye on how far it rotates after that, because we're going to measure that angle. Right? I'll record that angle. Right? So I'll do this with you guys. Do this with you guys. Right? If you need a couple of shots, that's all right. Okay. I'll do this up here, and then I'll pause the video and take a trip around the room, make sure everybody can do it. Okay. So I'm going to start my reverse belt on the x-axis. So this will be my 0 point. Okay. Maybe I'll get it going just to get it going. And when this crosses my start-finish line, at some point I'm going to hit start. Right. And then I'll time 3 revolutions. Right. Ready? And go. 1, 2, stop. Okay. Okay. And then I'll let it naturally slow to a stop. Oh, okay. You know what? That one now around almost exact. Man. Okay, here, I'll go with that.
We start the timer when we start spinning it.
Yes, start the timer when you start spinning it. And as soon as you take your finger off the turntable, you stop the timer. Okay. And then you let it naturally slow to a stop. Now mine went almost 1 revolution all the way around, but it's a little bit short. A little bit short. Okay. So I got 6 point something seconds. Okay, now hold on to that. Because before I move this, I do want to measure this angle. So here's my start stop line right here. You guys see my start stop line? Okay. And the coin almost went 1 full revolution, but it's a little bit short. So I'm gonna grab that angle. It's 10 degrees short. Guys, it's 10 degrees short. You guys see that? Right? Which means after I let it go, it went a further how many degrees? What's 360 minus 10? 350. You guys have that? Okay. So here, I'll show you guys where I'm going to record that on my paper. Okay. So the time to go 3 revolutions, 6 pi radians, was, I'm going to call that, I'm going to call that 6.8 seconds, which is this number right here. I'll just round it to 6.8 seconds. Okay? 6.8 seconds. Okay. Okay. Then I let it go. And it was just going. Okay? And in additional, did I say 350 degrees? Because it was almost 360, but it was 10 degrees short. Okay? But this says how many radians to come to a stop. So we need to convert. I have angle equals, now I know it's 350 degrees because I measured that with a protractor, but I don't want degrees. I want radians. Guys, how do I convert from degrees to radians? Or another way to say that is, how many radians is equal to how many degrees? Can I say 180 degrees is pi radians? Okay. Or you can say, could you say 360 degrees is 2 pi radians? Could you do that? It's the same thing. Right? Or if you want, you can even say 1 radian is 57.3 degrees. So that's close enough too. Okay. So however you get, let's say 350 times pi on 180. There. So I'm getting 6.1 radians. Okay, 6.1 radians. Okay, just like that. 6.1. Okay, good. All right, so let's recap what you guys saw. Okay. I watched the coin go around and come to a stop. I measured that angle to be 350 degrees. It was like 10 degrees short of a full revolution. That's how I know that. I measured that with a protractor. Okay. Okay. And then I said, well, I really want radians. So I'll multiply by pi over 180. And that tells me how many radians. And I take that number, 6.1 radians, and I put that on theta stop. So it took an additional 6.1 radians to slow to a stop. Okay. Okay. So I let it go for 6 pi radians, which is 3 revolutions, at a constant angular velocity, and I timed that. I got this many seconds. Okay, wrote that. Then I took my finger off, and it kept going. An additional so many degrees, which I converted to radians, got this many radians. Okay. Now here's where I'm going to pause the video and walk around the room and make sure that everybody's up to where I am. All right, we're back recording. Okay, so everybody's up to where I am. So here's a recap. You did 3 rotations at constant angular velocity. You timed that on the stopwatch. Then you let it go. And it kept going. And then because the friction eventually stopped, now you can measure that with a protractor in degrees. Then you said times pi over 180 to convert that to radians. So we have these measured values, right? These measured values. So let's do this. Let's figure out while you were spinning at a constant angular velocity, guys, if it went some angular distance with pi radians and some time, guys, how many radians and how many seconds? How do you get how many radians per second? What do you do with these numbers? Yeah, divide them. Yeah, because radians divided by seconds gives you radians per second. Isn't that true? Right. So I'm going to take my 6 pi. Guys, everybody right now on the calculator type 6 pi. Okay, because initially everybody had 6 pi radians. That was pretty revolution. Then divide by. You guys follow? 6 pi divide by. And then whatever the time interval was to do that. So this many seconds. Right? It went this many radians in that many seconds. I'm getting that 2.77 is my number.
Okay, so basically.
2.77 radians per second. That working out for you guys too? How many radians per second is how many radians per second? Right? Now, for the part, the second part of the story where we're slowed to a stop, there's a reason I called this number that you just wrote omega naught, because this is the initial velocity from the point of view of the equation where it starts to slow down. Right? You take your finger off, and it has this velocity, but then it slows down, and it goes to, guys, how fast is it moving right at the very end? Zero radians per second. Huh. It was spinning this fast. It moved this far before it finally came to rest. Hey, is that 3 kinematic values? I think that's 3 kinematic values. I think we're about to break these guys out. Oh, yeah. Oh, yes. Guys, do these 3 look just like these 3 from many months ago? Or, well, actually, all the time. We keep using these over and over in this class. They never go away. The only difference is, instead of like how far in meters does a car go, this is how far does the turntable turn in radians and so on. So instead of meters, we have radians. But otherwise, they kind of match, don't they? But linear speed is now angular speed and so on. So here's what I'm thinking is there's another time here. I guess here it says time stop. Now, I did not have you time this one. In fact, if you want to, I might recommend writing the side margin here, right? Calculation or calc for calculate. Okay. So this initial time you measure. I'll say measure. So you measure the first time on a stopwatch. And you got to calculate this time using using kinematic formulas. Okay. So calculate. Okay. Now, how can we get the time? I'll help you guys out here. It's going to be a 2-part process. Guys, here's our game plan. So you know initial final angular velocity is not true. It goes to 0. It starts spinning however fast you're spinning it. Okay. And you also know the angular displacement in radians, and it has to be in radians, but you have that because I just walk around chat. So everybody has these 3, right? Has these 3? Can you use that to calculate the angular acceleration, which should be negative because it's slowing down? And guys, once you have the angular acceleration, can you pop it up here and solve for time? That's the game plan. We're going to use this one to get alpha, and then take that alpha, pop it up here, and solve for time. That's the whole plan. Right, you guys ready to do that? Right. So I will do that with my numbers, and you guys do that with your numbers, and we're going to get some answers. So let's get this up. Okay, so we're playing off that. Start with omega final squared equals omega initial squared plus 2 alpha theta. And our goal right now is to solve for alpha. So I'm just going to 0 radians per second. So equals, now the initial angular velocity. Oh, well, that's what I said here. Initial angular velocity. Now mine is 2.77 radian per second. So let's go 2.77 radian per second. I'm going to square that plus 2 alpha we're solving for. And then for theta, guys, do you want degrees or radians here? Radians. Right. Oh, and I have that number of radians. It took 6.1 radians to come to a stop. So 6.1 radians. Okay. Can you guys solve for alpha? So just subtract, divide. Right. So in general, it would be negative omega naught squared over 2 theta. Okay. But then with the numbers, it goes negative 2.77 squared over 2 times 6.1. Okay. And this would be radians per second squared. Okay. Okay. And let's see what I get. Okay. Now, of course, your numbers are different than mine, but they should be kind of comparable. Okay. Should be too accurate. If you get a billion, there's probably something wrong. Maybe 2.77 squared divided by 261. Okay. So mine turned out to be negative 0.63 radians per second squared. That's my alpha right there. Negative 0.63 radians per second squared. Right? Are you guys getting something kind of in that ballpark? Now, if it came to a sudden stop, I bet this number's a lot bigger, like maybe -1 or -2 or something. If you have very low friction and it just spun forever, I bet this number might even be smaller than mine. But I had a pretty good spinning one, so yours is probably similar to mine or bigger. Okay. So I'm going to go to where it says alpha stop. You guys see alpha stop at the very bottom? And I gave you the negative to really help you out because everybody should be negative. It's negative, and mine finishes 0.63. And that's radians per second squared. Okay, radians per second squared. Okay. Okay, so everybody got their alpha also? Okay. Because once you got your alpha, your angular acceleration, now we can hop over to this second kinematic expression and solve for time. Right? What was the stopping time? Right? Now, I know mine kept rolling for a few more seconds, so I'm going to guess maybe like, I don't know, 4 or 5 seconds, somewhere in there, maybe. Here, we're going to find out. Omega final equals omega initial plus alpha t. Okay. Now we're solving for t, and I have everything else. So we're going to 0. Radian per second. It was spinning at, okay, omega naught is right here, of course, 2.77. 2.77, that's radians per second. Plus, and my alpha is actually negative 0.63 radian per second squared. That's right there. And then solve for times. Okay. So algebra, here, I'll throw in a little algebra step. Can I divide, subtract that and then divide by that? So negative 2.77 over negative 0.63. And the units work out as seconds. That would be the time. So time, this is time stop. That's what we're solving for the whole time. But stop. Stopping time. Right, so negatives cancel. 277 over 60. I'm looking at, oh yeah, look at that. Right? Now, of course, I just did this all in front of you, so I didn't know what the answer was going to be, but I did watch it slow to a stop, and I said, it's probably about 4 or 5 seconds. Didn't I just say that about a minute ago? So it's probably about 4 or 5 seconds. It totally is. It's right in that window. Yeah. I mean, that looks like a completely reasonable number. Right? The stopping time. Okay, after you let it go, it kept rolling until it came to a stop. It took that long. So where time stop is right here. I'm going to write that number in. How many seconds that is. Okay. Okay. Right. So I'm up to right here. Here, I'm going to pause this video again and take another trip around the room and check on you guys. All right. So everybody's up to where I am. Okay. So tomorrow we'll finish this, and just to plant some ideas by tomorrow. Do you guys see? We'll find its average value. We will. Guys, these are all linear values over here. So this is like, what's the story of this Roosevelt is going around in a linear sense. Okay. And then there's spaces for some graphs over here. We're going to make some graphs. Yeah, so we're going to save all that adventure for tomorrow.